Good afternoon. We were discussing the heat exchanger in last two classes. Well, we will continue the discussion. What we were discussing about the parallel and counter flow heat exchanger, simple shell and tube type. Let us start with that again. Let us have a shell and tube type like this, simple shell and tube, double pipe. This is the tube side fluid, and tube side fluid in and tube side fluid out. This is the shell side fluid in and out, shell side fluid, shell side fluid, shell side fluid. Let us also draw side by side the parallel counter flow arrangement. This one the parallel flow, the both shell side fluid and the tube side fluid flows in the same direction, but this is the I am not writing again the tube and this thing again. This is a counter flow type, shell end. Now, the temperature diagram along the length of the tube, if you see length or area, whatever way you think it, area, it is better because ultimately you will deal with the area for heat exchange, L or A. Here what happens, the hot side fluid, if we consider hot side tube or shell, doesn't matter, the hot fluid, not hot side, hot fluid has a decrease in temperature and the cold fluid increases the temperature in the same direction. Let us consider this is the hot and cold. Let this temperature, H is the subscript for hot I told, and 1 is the inlet here, parallel flow TH2 is the hot outlet. Similarly, cold inlet is TC1 and cold inlet is TC2. Then in this diagram we can show TH1, TH2, TC1, TC2. This is the picture. The assumption is that the fluid temperature is uniform across a section and heat is being, this is the hot fluid, sorry, this arrow I should show here, it will be difficult there, I will draw something else. This is the cold fluid, this is the hot fluid diagram temperature, this is the cold one, and at any section the heat is flowing like this from hot to cold. This is the temperature. Here the situation is this, the hot fluid flows like this from TH1 to TH2 in a direction. Let the similar way the hot fluid flows through the tube and the cold fluid flows in the opposite direction, for which this is known as counter flow, hot and cold. Here also the heat transfer takes place from hot to cold because of this temperature difference. Now this type of problem, this type of arrangement, one type of problem is like this. First of all, let us see that the energy balance or heat balance is like this. If I consider m dot H as the mass flow rate of the hot fluid and m dot C is the mass flow rate of the cold fluid, in both the cases m dot H and m dot C, with this nomenclature the total heat that is transferred between the hot and cold, m dot H, and if C stands for the specific heat at constant pressure, is TH1 minus TH2, that is the heat which is being given by the hot fluid equals to m dot c Cc Tc2 minus Tc1. Now, this is the first line of energy balance. Now, the one type of problem is this, that the conditions are like this. The property that Ch and Cc are usually known, thermodynamic properties, specific heat. Now, the operating parameters or conditions are that flow rate of the hot fluid, its inlet temperature, its outlet temperature, flow rate of the cold fluid, its inlet temperature and outlet temperature. Now, out of these 6 quantities, you see we have one equation only relating to these 6 quantities. That means 5 are independent and 1 is dependent. Usually, the mass flow rates of both hot and cold are given in some class of problems along with 3 temperatures. Means implicitly I know the 4th temperature. That means all these 6 quantities are given. This type of problem means that the rating of the exchanger, that means the operating conditions as far as the heating and cooling load, that means how much heat has to be transferred from the hot fluid to be cooled or how much heat has to be gained by the cold fluid to be hot, is known, because the mass flow rate and the temperatures are all known. 3 temperatures are known, along with the mass flow rate I can find out the 4th one. So that this is known as, in this terminology, in the field of heat exchanger, the heat exchanger is rated for its heating and cooling load. What is to be found out for this type of problem? We are interested to find out what surface area is required. If we consider a simple double pipe heat exchanger, either parallel or counter, what is the surface area required? This is known as sizing problem. Means the heat transfer from the heat load side is rated. That means the total load is given. How much heat has to be transferred is given. We want to know the size. Size means the surface area required for that heat transfer. This we can find out definitely if we write this equation, Q is equal to UA delta Tm. Just I discussed last class that we know overall heat transfer coefficient. The concept of overall heat transfer coefficient was told earlier, which is the sum of the heat transfer coefficient of fluid sides, both the sides fluids plus the conduction resistance. And if we see the resistance, that sum of the resistances are the equivalent resistance, if we assume that overall heat transfer coefficient is constant along the flow, then we can write the rate of heat transfer in this fashion: UA delta T, some mean temperature difference, where A is the area based on which overall heat transfer coefficient is defined. That means basically this is the definition of overall heat transfer coefficient, but it is other way in practice. The overall heat transfer coefficient is given, so that practical problem we have to find out the area based on which EU is given when we know the Q. But the only difficulty here, compared to simple convection problem as you have done in the class, that this temperature difference, sometimes we have seen the flat plate, free stream, all are constant temperature along the flow. But here this delta T responsible for heat transfer changes from one section to other section. Here it is inlet and outlet because both are flowing in the same direction. Here from one section. That means there should be some mean delta T, mean of these two extreme difference of delta T. This is one delta T, this is another terminal. The mean of terminal delta T in such a way that could define this equation. So to find out that delta Tm, we have to do a small mathematical exercise. Let us consider the parallel flow case and a elemental area in this exchanger dA, where we have a change in hot fluid temperature, which is denoted by dTH, and also this is a decrease in the temperature, and at the same time there is an increase in the cold fluid temperature through that dA area here in the exchanger, through which the change is dTc, and here there is a amount of heat transfer delta Q, which is represented here. We can represent here also delta Q. That means a small elemental area delta dA, delta Q heat is transferred from the hot to cold, by which the hot fluid suffers a differential decrease in temperature dTH, and the cold fluid suffers a differential increase in temperature dTc. Then we can write that del Q is equal to m dot HCH into minus dTH, because TH is decreased, is equal to m dot CCC dTc. This decrease and increase of temperature with reference to the direction of one particular prescribed direction, and here the prescribed direction in a parallel flow is the direction of flow, because both the fluids are flowing in the same direction. Then we can consider that change in hot fluid temperature is a decrease and it is an increase. And it is interesting to see that if you integrate this equation, you get this one, because if you integrate this minus dTH in the direction of the flow, it will be TH2 minus TH1 is dTH. So minus of that will give this, and dTc will be TC2 minus TC1. That means simply a differential form of this equation we are writing here. Okay, now we make a very simple algebraic, at a primary school level algebraic manipulation, that dTH minus dTc equals to what? dTH minus dTc is del Q. dTH is minus, dTc is also minus, that means minus del Q 1 by m dot HCH plus 1 by m dot CCC. dTH minus dTc, clear? This can be written as d of TH minus TC is algebraic step minus del Q 1 by m dot HCH plus 1 by m dot CCC with the nomenclature I have told. Now from the definition of heat transfer by this equation, the overall heat transfer coefficient, we can write del Q at that section is UdA into TH minus TC, because TH and TC are the hot fluid and cold fluid temperature at that section, infinite small section of infinite small area dA. So this has to be valid. So therefore I can substitute del Q here, and I can write d of TH minus TC, very simple, divided by TH minus TC is equal to minus U dA, dA I will write here, m dot HCH plus 1 by m dot CCC into dA. Clear? Okay. You may or may not take the note. This is given in any textbook. Just it will also be good that if you just go on seeing, can find out any inadvertent mistake if by chance I make. It's not always necessary to take the note, but you can take also the note because it is given in any book. You see the philosophy. So this is all right. Now if you integrate both these sides with respect to dA, so left side represents the temperature difference. This is the way it is expressed between this inlet and outlet with respect to this parallel flow heat exchanger. Then the left hand side become ln TH minus TC, it will be TH2 minus TC2 divided by TH1 minus TC1. Okay? Any problem you can ask me. Okay? And this side will be minus U 1 by m dot HCH plus 1 by m dot CCC times area. Okay? So this is clearly this thing. Now I will substitute 1 by m dot HCH and 1 by m dot CCC from here. There are two equations. If you consider Q into picture, Q is this and Q is this. That means this equality gives 2, and ultimately I can substitute 1 by m dot HCH plus 1 by m. What is 1 by m dot HCH? It is Q TH1 minus TH2 by Q, and m dot 1 by m dot CCC is TC2 minus TC1 by Q. And if you do it, it's very simple, then you get this, ultimately this equation, and Q will come. Q is equal to UA TH2 minus TC2 minus TH1 minus TC1. I am not unnecessarily wasting time by doing this. Just simple, if you do that, you will get this one, TH2 minus TC2 divided by TH1 minus TC1. Automatically you will get this. If you just substitute 1 by m dot HCH plus 1 by m dot CC in terms of Q from here. That means here the entire thing is a mean temperature difference, delta T. Now if I define delta T2 as the temperature difference at the outlet here in case of parallel flow, that is equals to TH2 minus TC2, and delta T1 is TH1 minus TC1, then this can be written as Q is equal to UA delta T2 minus delta T1, and it will be always positive whether delta 2 and delta T1 vary with their respective magnitudes, higher and lower, because plus minus will be adjusted. If delta 2 is more than delta T1, both numerator denominator will be positive, and if it is other way, both are negative. Okay, so therefore we can write this equation like this, and this quantity is known as LMTD, that is log mean temperature difference, because the log is coming log mean temperature difference. The log mean temperature difference, LMTD, which is defined as delta T2 minus delta T1 divided by, that means this fashion, the difference of the two delta T's at two terminals divided by the ln of their ratios. This is LMTD. So Q is equal to, therefore you see that if the exchanger is rated fully by its heating and cooling load, prescribing this thing so that I know Q, then I can find out its surface area if I can determine LMTD. So if I know the definition of LMTD, which satisfies this equation, that means it is that average delta T between the two terminals which satisfies this equation. And if I am provided with the value of the overall heat transfer coefficient, I can determine the size of the exchanger. This is known as typical sizing problem. Clear? Clear to everybody? Now there is a clue. If, very important, it is a counterflow heat exchanger, how you will derive it. Now first of all, counterflow heat exchanger is also the same formula, but what is delta T2? For a counterflow heat exchanger, the generic formula is this one. Delta T2 in counterflow heat exchanger is any side you can take in counter flow heat exchanger. There is no inlet outlet reference because it is hot fluid inlet, it is cold fluid inlet. Let us make this delta to TH2 minus TC1. Then delta T2 will be TH2 minus TC1. And what will be delta T1? Delta T1 will be TH1 minus TC2. Clear? How to derive it? I leave it to you as an exercise, very simple. How to derive this one? That means I have to come to this step where this will be UA into TH2 minus TC1 minus TH1 minus TC2 divided by ln TH2 minus TC1 divided by TH1 minus TC2, so that a generic formula will come out. LMTD is delta T2 minus delta T1, difference of delta T's divided by ln ratios of delta T's. How to do it? Very simple. I tell you the catch because I will not waste time. Here in this equation, if you take here one prescribed direction here positive, then DTH will be minus because it is decreased in this direction. Take the flow direction of hot fluid. Then DTC will be also minus. Because why? Because this is increasing in the negative direction. So therefore, both the things will be minus. It will be minus DTH, it will be minus DTC. So therefore, DTH minus DTC will be changed, which will be del Q 1 by m dot c dot minus 1 by m dot h ch. Change will be there. So accordingly, you can find out that there will be changes. Just only changes here. Very simple. That means this equation will be minus DTH and minus DTC. And think that if you integrate this, you will get the same result. This is clear because this is a energy balance, all are scalar quantities. Counter flow, if you integrate this minus DTH, DTH will be, this is a preferred, that is a positive direction. DTH will be TH2 minus TH1. So minus DTH is TH1 minus TH2. Similarly, DTC will be TC1 minus TC2. So minus DTC will be TC2 minus TC1. Therefore, integration of this with minus DTH and minus DTC for counter flow will give you the same result. So finally, when you will substitute this 1 by m dot CCC minus 1 by m dot HCH, because this will come, then you take the same equation. Only catch is that you have to express DTH minus DTC because D of TH minus TC, hot minus cold. Clear? So this is an assignment, everything I have told, that in a counter flow also you can do the same thing. But now the most interesting part of this equation, very interesting and very important too. I think you are intelligent, you can understand. Now the situation may come, two things you must remember, that a counter flow, parallel flow heat exchanger, if a heat exchanger is very infinitely long, this may be equal to this. Cold fluid outlet temperature can at best become equal to the hot fluid outlet temperature I have told earlier, but not the hot fluid inlet temperature. But here, the cold fluid outlet temperature may be more than the hot fluid outlet temperature even in a finite length, because here you see this temperature, there is no restriction that this will be lower than that, because heat is transferred this way. That means at this end of the heat exchanger, the temperature differential causing the heat transfer is from the inlet temperature of the hot fluid to the outlet temperature of the cold fluid. So as because they are flowing in the opposite direction, the cold fluid outlet temperature may be more than the hot fluid outlet temperature, which is not the case for the parallel flow. Another thing is there, if the product of M and C, M dot and C for hot and cold fluid becomes same. That means if M dot HCH is M dot CCC, their will be a situation for counterflow. The two curves will be parallel to each other, and ultimately delta T2 is equal to delta T1 is equal to delta T. So what is LMTD? What is LMTD? What is LMTD? Gone. What is LMTD? Anybody? Who told delta T? How? 0 by 0 form. So you can use the L'Hospital's theorem, taking the limit. In many ways you can prove it, that it will be delta T1 or delta T2 or delta T. Very simple to prove these things. That is also left to you. We can take delta T2 by delta T1 as x. You can write delta T1 into x minus 1 divided by ln x. Limit as x tends to 1, you will see this becomes delta T. Okay. So therefore, we can do it in various ways. X minus 1 by ln x, L'Hospital's theorem is a mental problem. X minus 1 becomes 1 and ln 1 by x, and in that case here it will be delta T1. This thing will be delta T1 into x minus 1, where x is delta T2 by delta T1, and we can write the denominator as ln x. Now limit of this as x tends to 1, sorry, not limit of this as x tends to 1, we have to make a L'Hospital's theorem differentiation. Again it is 0 by 0 form until the 0 by 0 form gone. So we have to go for number of steps with that. So delta T1 divided by ln x is what? 1 by x. And limit x tends to 1. That means there are various ways to prove it. Sometimes you can prove that delta T2 minus delta T2 is delta T1 plus epsilon, and put it and take epsilon tends to 0. Denominator ln 1 plus x you can expand in a series ln 1 plus x type of thing, that is delta T1 by epsilon, and you can prove that limit will be delta T1 only. So therefore it is very important, these are school level tasks, that when delta T2 and delta T1 are same, under these circumstances mass flow rate capacity product is equal, then we have to have LMTD as this. And one information I give you in this respect, just an information, this can be proved analytically, but I am not going to prove, just as an information for an engineer. If delta T2 by delta T1 vary by a factor, ratio, which one is greater, depending upon that the ratio is within 2.2, then we can use the arithmetic average as the LMTD with 95% accuracy. Usually arithmetic average is higher than the LMTD. We should not use it, otherwise it will be over predicted. This will be over predicted. So therefore, LMTD and arithmetic average will be within 5% error, provided delta T2 and delta T1 varies. Varies means the ratio is within 2.2, and when exactly this is 1, ratio is 1, they coincide with each other. That means arithmetic average is equal to the LMTD, because arithmetic average is delta T1 or delta T2. Clear? Now another interesting thing comes now into picture, that in this rating given, sizing problem is very simple. But if it is other way, that means I tell only m dot h, m dot c, th1 and tc1. Neither th2 nor tc2 is given. That means this is not rated. But I know A. This is known as rating problem. Two types of problems, sizing and rating. Sizing problem is the earlier one. The entire heat load is given. Q is known. That means explicitly m dot h, m dot c, th1, th2, tc1, tc2. Of course, these four are not required. Tc1 is given, Tc2, all known. Then we find out the area, we know the LMTD. So, LMTD, using the LMTD method we can find out. But if it is other way, area is given, now this delta Tm is now LMTD, okay, and LMTD is what? LMTD is delta T2 minus delta T1 by ln delta T2 by delta T1, okay. Now, if I know only these two, TH1, TC1, not TH2, TC2, this equation cannot tell anything. So, how to find out this? We cannot know LMTD. So, this type of problem where the sizing is given, but we have to rate the exchanger, means a particular exchanger with a given surface area is suitable or not, then what we have to do? We have to use an iterative method. That means the area is given, we have to rate the exchanger, whether it will be suitable. What is this rating? We have to assume. I will solve a problem today, it will be more clear, but still I am telling now, you can under either TH2 or TC2, any one we assume first. If you assume TH2, TC2 will be found out from this equation. Both are assumed value. Then you find out LMTD, obviously with this assumed value. Then with this LMTD, since A is known, we find out Q. Now with that Q, we iterate, that means we refine the value of TH2. Clear? So this way we do both TH2 and TC2 until they converge with each other. That means the new value is close to the earlier value, very simple. So today it is nothing, but when it was discovered long back, there was no MATLAB, no program, even not a calculator even. So therefore people thought that it is tremendous stuff, an iteration method by hand, even without a calculator, whereas the sizing problem is explicitly found out with a slide rule even. It is not done. So therefore a difficulty was faced in this case, that LMTD method is not that suitable because it requires tedious iterations, and your gauge value is not very close. You have to go for number of iterations to convert the solution. Today it is a laughing stock, but it was there when it was discovered. Then two scientists, Case and London, they are two stalwarts in the field of heat transfer, they found out another suitable method for this type of problem, where sizing is given, that means surface area is given, we have to rate the heat transfer in terms of its heating and cooling load. That means we have to tell what are the outlet temperatures of the hot and cold fluid. And this method, which was found by Case and London, is known as NTU epsilon method. NTU epsilon method. So LMTD is one method, another method NTU. An employer in your what is called that, your placement, placement interview will ask this thing only, that when NTU epsilon method will be used, when LMTD, what is the difficulty of LMTD in rating problem, and why NTU epsilon method is difficult for sizing problem, that also I will tell. Both the methods have relative merits, demerits. Now NTU epsilon method. Now what is NTU? NTU, I will tell you afterwards when the course of deduction it will come, but now you know the meaning of NTU. It is an abbreviation, number of transfer unit, NTU, and I will come this afterwards, because now if I write the NTU expression like Nusselt number HD by K, you will be nowhere to why unnecessarily all this, because automatically in the way of deduction a term will come which is a non-dimensional term known as number of transfer unit. Epsilon is known as effectiveness, which is also a non-dimensional term, effectiveness. And this effectiveness of an heat exchanger epsilon is defined as Q, that is the heat transfer actual, by Q maximum, means ideal, that is the maximum. actual discharge by the ideal discharge is the coefficient of discharge, this type of thing, the maximum and actual. What is actual heat transfer? This is this. M dot H CH, the temperature change. This is the actual heat transfer. But what is the maximum heat transfer which is possible? Now, maximum heat transfer, if you write Q max, try to understand this. Again, there is a concept. Many people, you can make people nervous by asking one question. I will tell you that maximum heat transfer will be associated with the maximum change in the temperature. What is maximum change? That is TH1 minus TC1. That means, let us consider the counter flow. I will tell the maximum heat exchange will be possible when the cold fluid will attain the inlet temperature of the hot fluid. That is the maximum temperature available in the exchanger. Or other way, the hot fluid will be cooled to the inlet temperature of the cold fluid, which is the minimum temperature of the heat exchanger, which means the Qmax will be associated with the maximum temperature difference TH1 minus TC1 of the exchanger. But there is a clue. Hot and cold fluid physically will not attain simultaneously the TH1 minus TC1. It depends upon their capacity. That means the product of M dot and Cc. The fluid for which this M dot C is minimum, that will catch it first. Afterwards, the heat exchanger operation will stop. So therefore, it is written in a generic way, M dot C minimum, which may be either M dot C Cc, that I have to calculate from the value. I have to calculate from the value, the specific heat values and the mass flow rate values. Clear? That means the ideal or the maximum heat transfer is defined as minimum capacity rate or minimum capacity, that is mass flow rate times the specific heat capacity times the maximum temperature change. One thing, this is never achievable in a parallel flow. In a counter flow, like a reversible process, it can be achievable if we make an infinitely long exchanger. In a limiting case, like a quasi-static process, that in a limiting case TC2 will reach TH1 or TH2 will reach TC1 if you give an infinitely long. But here, even if you give an infinitely long exchanger, it will never reach. Delta S universe can be 0 in an ideal situation of reversible process, a quasi-static process, but can never become less than 0. It is impossible. So therefore, in a parallel flow heat exchanger, it is never possible, not feasible at all by the physics. So then what happened? This happens like that. This definition of effectiveness can be understood, conceived with respect to a counter flow heat exchanger. Nevertheless, as a criteria of comparing the exchanger with this effectiveness, we will use the same for parallel flow also, though it does not have any physical meaning like the ratio of actual to maximum heat transfer in that case. Is it clear to everybody? Good students? Okay. Now, if I consider the cold fluid is the minimum fluid, then what is epsilon? Now, if cold fluid, if M dot Cc is minimum, then what is this epsilon? It is, what is epsilon? You tell me, if this is minimum, then M dot C Cc into TH1 minus TC1. And in that case, I will prefer to write this Q, this equation. Why? Because this thing will cancel. Cc into TC2 minus TC1 cancels out. Similarly, if M dot HCH is minimum, then epsilon is M dot HCH in TH1 minus TC1, and I will write then here this one, M dot CH as TH1 minus TH. And ultimately this will cancel, TH1 minus TH2 divided by TH1 minus TC1. So from here I can make another definition in terms of temperature change, which will be more convenient, and parallel flow exchanger will be little comfortable with this definition. It is the ratio of the temperature difference or temperature change of the minimum fluid means minimum capacity fluid, divided by the maximum temperature change of the exchanger. I think parallel flow heat exchanger will be much comfortable, that the definition via heat transfer is gone. That means it is the change of temperature for the minimum capacity fluid divided by the maximum temperature change available in the exchanger. Clear? Okay, very good. Now with this I will go for a simple algebraic deduction. Let us go back to our, what is that, to our earlier deductions, where we came here ln TH2 minus, now we consider the parallel flow arrangement again, TH2 minus TC2 divided by TH1 minus TC1 is equal to, if you I remember correctly, 1 minus u by a, just one step ahead, m dot c cc plus 1 by m dot h ch, where after this was replaced from there and I got an expression for LMTD. But if I stop here in that deduction, I just change the root. Let us write this TH2 minus TC2 divided by TH1 minus TC1. You just follow. You may not have to take note because it is given in the textbook. You may or you may not take, but follow it. Because deductions, if you logically follow afterwards, also taking notes you can follow, then you will be able to deduce for a new condition, is equal to, just I write this thing in an exponential function, nothing great, minus UA, and here I will make some assumption before doing, because it is case by case. In a parallel flow, I first assume the cold fluid is the minimum fluid. That means m dot c cc is the minimum. The catch you will know afterwards. First accept it. So here sir accepts that cold, this is minimum, the product is less than this product. Then I take this as common, m dot c cc. When I will tell the case for which m dot h ch is minimum, then you will take m dot h ch as common. I will tell you. Then it will be 1 plus m dot c cc divided by m dot h ch. Okay. Now we have to play with this. Now here this equation is always used. Here what we will do, we will express TH2 in terms of TH1. What is that? Write that TH2 is equal to, from here, TH2 will be TH1 minus m dot cc divided by m dot c, sorry, m dot hch, m dot ccc, m dot hch, TC2 minus TC1. I think I have done correctly. That means the trick is that TH2 is substituted in terms of TH1 and TC2 TC1. TH2 chalega nahi here. You will understand why. All these tricks will be understood at the end. Now, if you substitute this at the present moment, you accept that this way it has to be done. Only follow the algebraic continuity. TH2, then I can write here TH1 minus m dot c cc divided by m dot hch Tc2 minus Tc1, Tc2 minus Tc1 minus Tc2. So, Th2 minus Tc2 minus Tc2 divided by Th1 minus Tc1 is equal to exponential, this space is not utilized, UA by m dot c Cc 1 plus this one m dot c Cc divided by m dot h Ch. So, what I have done, the left hand side Th2 minus Tc2, Th2 I have substituted by this. Okay. Now, what I do, minus Tc1, here I add. That is why I am writing plus, because there is no place to write that. Some teacher intelligently, tactfully give a space. So, minus Tc1 and plus Tc1. So, what does it look? Th1 minus Tc1, okay, minus 1 plus this into Tc2 minus Tc1. So, if you divide it by this, let me write that Th1, oh God, Th1 minus Tc1 minus Tc2 minus Tc1, Tc2 minus Tc1 into 1 plus m dot c Cc by m dot h Ch and divided by Th1 minus Tc1. Just follow it. Right hand side I am not writing. So, this becomes is equal to 1 minus, since I have considered from this step after approaching further, where this here approaching to this step, that the cold fluid is the minimum fluid. That means Tc2 minus Tc1 by Th1 minus Tc1 is the effectiveness, epsilon, because change in temperature of the minimum fluid divided by the maximum change in temperature. Clear? So, therefore, this will be 1 minus epsilon into 1 plus m dot c Cc divided by m dot h Ch. This equals to this exponential. So, if you equate this and write this epsilon, then you will get this expression. Here I will write, where I will write this one. Here, if you now equate this 1 minus epsilon 1 plus this by this with this, you get finally an expression that epsilon is equal to 1 minus exponential minus UA by m dot c Cc into 1 plus m dot c Cc divided by, no sorry, what is that? Okay, m dot h divided by in terms of this quantity. Clear? Now, here m dot c Cc is the minimum heat capacity. Now, this term minus UA by m dot C minimum is known as number of transfer unit, NTU, which is a dimensionless term. Overall heat transfer coefficient, surface area of the heat exchanger divided by m dot into C minimum. Now, if you can ask me the questions. You should ask this question to me without gossiping or chatting with your friends at the back. Sir, if the hot fluid is the minimum fluid, what could you have done? Now, if the hot fluid is the minimum fluid, first I tell you, this expression will be same, just m dot c and m dot h will be interchanging with each other, so that in a generic formula I can write in terms of m dot c minimum and m dot c, generic formula. So this will interchange. If m dot h ch is the minimum, then it will be m dot h ch. NTU is minus UA by m dot c minimum. This will be NTU, and this will be 1 plus m dot c minimum by m dot c. Similarly, it will be 1 plus m dot c minimum by m dot c. But how to do it? Just interchange. Here I will start again. I started with cold fluid as the minimum fluid, hot fluid as the minimum fluid. I will take m dot h ch. This is not all. I will first take. Secondly, I will not TH2, that is the second catch. Here TH2 will not be substituted from this equation, TC2 will be substituted. And in that case, TC1 will not be added, subtracted. TH1 will be added and subtracted. This is having a rhythm. Good boys can understand this thing better immediately by intuition. Here we will take m dot h ch as common. Then it will be 1 plus m dot h ch by m dot c c c. Here TH2 will remain as it is. TC2 will be replaced in terms of other temperatures from here. TH2, TH1 and TC1. And after that I will add and subtract TH1. And in that case I will use the definition of epsilon as TH1 minus TH2 divided by TH1 minus TC1, because the definition of epsilon is the change of temperature for the minimum fluid and the change of temperature, maximum change of temperature available in the heat exchanger. Now, if you write in a very generic fashion, this will be like this. A generic expression is like this. If I make a very shortcut compact form by defining a parameter, just now if I define it like this, m dot c as the capital C, that means the capacity rate or simply the capacity, and m dot C, m dot cc, cc is the cc, and m dot h ch is equal to ch, and if I define C as the ratio of C mean by C, which may be either this by this, that means this by this, or this by this, depending upon the case. In that case, the expression will be very simple. It looks like simple, expression remains same, 1 minus exponential minus NTU, where NTU is minus UA, sorry, not minus, sorry, NTU is a scalar quantity, dimensionless, m dot C minimum, that means C minimum with this nomenclature, where NTU is NTU into 1 plus capital C, and therefore here it is 1 plus capital C. This is the expression, where capital C is the ratio of the total capacity, that means m dot C, specific heat, ratio of the total capacity. What is the ratio? Minimum to the other one, that means C mean by C. So this is the expression, and this expression is for parallel flow. Counter flow expression will be again a tricky, and that I leave to you to do the counter flow expression. In both the cases, that is left as an exercise, and the expression will be epsilon is equal to 1 minus exponential function of minus NTU into, here it will be 1 minus C, and here it will be 1 minus C into again exponential minus NTU into 1 minus. Now you see that in condensation and boiling, I told one of the fluids will be parallel. In case of condensation, the hot fluid is a parallel line. In case of boiling, the cold fluid is a parallel line. And parallel line means temperature does not change. And I told qualitatively that counter flow and the parallel flow remain same. But now mathematically you see that for a condensation and boiling problem, this one of the fluid specific heat tends to infinity. The fluid which is boiling and the fluid which is condensing, C infinity, I showed you earlier in the figure, which means that C is equal to C mean by C. That means this higher C tends to infinity, because which tends to infinity, that will be always higher. No question of calculation. That means an intelligent boy will tell that for boiling condensation, the ratio which you denote as C will be always 0. And if you put C 0 in both the expression, we will yield the same value. Epsilon is 1 minus exponential minus NTU. This is the argument, NTU. If you put C 0, because the ratio is always 0, because the higher heat capacity rate, whatever we call the product of m dot C, is tending to infinity, which is a hot fluid, cold fluid ka mamla nahi. It is not hot fluid, cold fluid. Which one is higher, which one is lower? Okay, clear? But here one thing is very much open, that if I do not know the temperatures explicitly, then what we can do, when we know the NTU, because area we know, overall heat transfer coefficient we know, and the mass flow rate and specific do we know, we can straight away find out the effectiveness. And when the effectiveness is known, I can find out the temperatures. Clear? So therefore, this is a case where the rating will be done explicitly, no iterations. Rating means the size is given, we have to find out the heat transfer. That means all 4 temperatures are not known explicitly. Clear? Any problem? Okay. So we can find out the epsilon, and say, whenever we find out the epsilon, okay, TH1 and TC1, all right, chalega. Then from the definition of epsilon, I can find out the temperature difference of the minimum fluid. That means heat load aa jayega. The temperature difference of the other fluid will also come. So therefore, where rating heating load and cooling load is not done, but size is given, NTU epsilon method is an explicit method. To find out effectiveness, fatafat temperatures are found. But where the temperatures are given, sizing is to be made. LMTD is useful because from here, knowing epsilon, NTU as a function of epsilon will be little difficult. You understand? This may require tedious calculations or iterations.